Use bigger method or penalty method to maximize z equal to 6x1 plus 4x2 subject to 2x1 plus 3x2 less than or equal to 30, 3x1 plus 2x2 less than or equal to 24, x1 plus x2 greater than or equal to 3, x1 greater than or equal to 0, x2 greater than or equal to 0. Now in order to do this problem by bigger method, the first step that we have to do is standardization. In the standardization, we are converting the maximization problem to a minimization. If the problem is given as a minimization one, we have to get it converted to a maximization problem. Here already the question is given as a maximization problem itself, so no change is required in the initial stage. Now we are going to consider the constraints one by one. The first constraint is a less than or equal to inequality. So we have to make it an equation. In order to convert this less than or equal to inequality to an equation, we make use of slack variable. So here the slack variable S1 is added to the left hand side of this less than or equal to inequality to make this as an equation. We know that slack variable is a non-negative variable, so slack variable satisfy the non-negativity restriction, and the cost associated with the slack variable is 0. Now the second constraint is also a less than or equal to inequality, that is also converted to an equation with the help of the second slack variable S2, and for the second slack variable S2 also we have the cost associated is equal to 0, and the second slack variable S2 also satisfy the non-negativity restriction. Now coming to the third constraint, we have the constraint as a greater than or equal to inequality. So for the greater than or equal to inequality, we have a surplus variable. So the surplus variable is a non-negative variable subtracted from the left hand side. Surplus variable is S3 here. It is also a non-negative variable. It is subtracted from the left hand side of the greater than or equal to inequality in order to make it an equation. So we added two slack variables and one surplus variable. But the problem is, we have to generate an initial basic feasible solution to the problem. Now in order to get an initial basic feasible solution to the problem, we cannot use this surplus variable. So in order to have the initial basic feasible solution, we add another variable called artificial variable we add artificial variable to the third constraint, or to the constraints where we have subtracted a surplus variable, we are adding an artificial variable. Artificial variable is also a non-negative variable, but it has got a cost equal to minus m. So we attach here a cost minus m to the artificial variable in the objective function, and this m is a very large positive quantity. Okay, so that is why the name bigger method, and the penalty method is also according to the strategy that we adopt in this particular method. Now the initial basic feasible solution. Here there are 6 variables. There are 3 constraints or 3 equations only. Hence we set n minus m unknowns equal to 0. So this is how we get the basic solution. N minus m is equal to 3, so we have to set 3 variables equal to 0. So x1, x2 and s3 are set equal to 0. The variables that are already in the problem and the surplus variable are set equal to 0, and these variables we call them as non-basic variables. Then once we have x1, x2 equal to 0, s1 is equal to 30, s2 equal to 24 and a1 equal to 3. So we have the initial basic feasible solution. Now let us write the simplex table. The first column is CB, the second column is the basic variable. Then we have, I am putting it as y1, y2, y3, y4, y5 and y6. This y1 corresponds to the coefficients of x1, y2 corresponds to the coefficients of s2, then y3 corresponds to the coefficients of s1, y4 to the coefficient of s2, then y5 to the coefficients of s3 and y6 to the coefficients of a1. Now we are going to write the cost associated with y1. Cost associated with y1 is 6. These are obtained from the objective function, maximization objective function. 6, 4, then S1 cos 0, S2 it is 0, S3 also it is 0, and A1 cost is minus M. Then the basic variables are S1 with value equal to 30, S2 with value equal to 24, and A1 with value equal to 3. Then the cost is CB is 0, 0 minus M. Now let us take the coefficients of x1 from each of the three equations. So 2 is the coefficient of x1 from the first equation, 3 from the second equation, and 1 from the third equation. Then 3, 2, 1 are the coefficient of x2 from the three equations. Then 1, 0, 0 are the coefficients of S1 because S1 is present only in the first equation. 0, 1, 0 form the coefficient of S2 because S2 appears only in the second equation. Then 0, 0, minus 1. These are the coefficients of the surplus variable. Then we have 0, 0, 1 as the coefficients of A1. Now you can note that S1, S2, A1 in this proper order form an identity matrix. See here 1, 0, 0, 0, 1, 0, 0, 0, 1 that form an identity matrix of order 3. Now let us find the net evaluations. Z is equal to, so for finding the value of the objective function Z, we use the relation CB into XB. So 0 into 30 plus 0 into 24 minus 3m. So that is the value of the objective function in the first iteration. Now we need the net evaluations. We need Zj minus Cj. They are obtained as CB, Yj minus Cj. So CB column minus the column for which we are finding the net evaluation minus the cost written on the top. So 0 into 2 plus 0 into 3 minus 1 into m. So that is minus m, then minus 6. Then we have next net evaluation 0 into 3 plus 0 into 2 minus m. Again we have minus m minus 4. Then we have 0, 0, 0 minus 0. Then next net evaluation is also 0. Next net evaluation is m, and the last net evaluation is also 0 because it is minus m plus m. Okay, so we have all the net evaluations. Now since there is a negative net evaluation, that's an indication of that's an indication that the solution can be still improved. Okay, so we need to take the most negative net evaluation. We need to identify the most negative net evaluation, and therefore minus m minus 6 and minus m minus 4 are getting compared. The most negative net evaluation is minus m minus 6. So we choose this minus m minus 6 as a most negative net evaluation. So we make this minus m minus 6 enter the basis. Now when one variable enters the basis, one has to leave the basis. That leaving vector or the leaving variable is determined with the help of minimum ratio rule. So the leaving vector is determined by minimum ratio rule. And minimum ratio rule is, we are calculating xbi by yij provided yij is greater than 0. So this is how we find the ratios. Numerator values are the xb column values. Denominator values are the corresponding values in the entering column, provided the denominator values are strictly greater than 0. So we are comparing the ratios 30 by 2. Then we have 24 by 3 as a second ratio. Then we have 3 by 1 as a third ratio. And we know among the 3 by 1 is a minimum ratio, and therefore we make this third row leave the basis, or correspondingly A1 has to leave the basis. Okay, and hence we are going to make the next modification. So we are writing the new basis. S1 is a first variable, it has no change. S2 is a second variable, it also has no change. Then in place of A1 we have the first, in place of a1 we have the first variable x1. So the new basis is s1, s2, x1. Now the cost is 0 is a cost for s1, 0 is a cost for s2, and for x1 the cost is 6. The x1 the cost is 6. So 6 is a cost for x1. Now all the remaining calculations are to be done with respect to the operation that we do in elementary row transformations. So we are going to do the remaining modifications. Now see, the entering column and the leaving row. The junction point determines the pivotal element. So this is a pivotal element, and in the next iteration that is to follow, we have to make the x1 as a third column of the identity matrix. S1, S2, x1 should form the columns of identity matrix of order 3, and x1 forms the last column of the identity matrix of order 3. Therefore its elements should be like 0, 0, 1. So in order to make the elements as 0, 0, 1, we are going to make the sufficient modification so that this column 2, 3, 1 is getting modified to 0, 0, 1. So that's what we are doing here. Now since this pivot element is already equal to 1, we don't have to make any modifications in this row. Just divide throughout by 1. So that leaves a row as it is. So first element is 3, then 1, then 1, then 0, then 0, then minus 1. I am just leaving this last column because this last column corresponds to A1, and A1 has already left the basis and it will never re-enter the basis because we have given a cost minus m, where m is a very big positive quantity. Okay, so that's why we say that it will never re-enter the basis. So it's not mandatory that you have to compute this column again. So we are just crossing it off. Now let us modify the remaining basis. Now we have to make this 3 equal to 0 with respect to this one. So let me call this last row as R3, and we are going to make the modifications of the remaining rows with respect to R3. So R2 gets modified as R2 minus 3 R3. R2 minus 3 R3 will make this 3 equal to 0. So let us make the corresponding modifications. 24 minus 3 into 3, that is 24 minus 9, it is 15. Then 3 minus 3, it is 0. Then 2 minus 3, it is minus 1. 0 minus 0. Then 1 minus 0. 0 minus minus 3, it is 3. Now we are going to make suitable modifications to R1 with respect to R3. So R1 minus 2 R3 will make this 2 equal to 0. So corresponding row gets the same change. So S1 gets modified as 30 minus 2 into 3. 30 minus 6, it is 24. Then 2 minus 2, it is 0. 3 minus 2, it is 1. Then 1 minus 0, then 0 minus 0, then 0 minus minus 2, it is 2. So we got the rows, got the entire second iteration values. Now let us calculate our net evaluations, value of objective function, etc. So Z is CB XB, and therefore 0 into 24 plus 0 into 15 plus 6 into 3 equal to 8. Now the net evaluations, 0 CB YJ minus CJ, they are the net evaluations. So 0 into 0 plus 0 into 0 plus 6 into 1 minus 6, it is 0. Then for the next net evaluation, 0 plus 0 plus 6 minus 4, it is 2. Then 0 plus 0 plus 0 minus 0, it is 0. Then we have 0 again, then we have minus 6. So we got the second set of net evaluations. Now this second iteration also leaves us with a negative net evaluation, so that's an indication that the solution can still be improved. So we have to make the solution, we have to improve the solution. So in order to do that, we make the variable corresponding to the negative net evaluation. There is only one negative net evaluation, so we have no choice but to make this variable, that is S3, enter the basis. So we make S3 enter the basis. Now we do the minimum ratio rule. We have to compute 24, the ratio 24 by 2. Then we have to consider 15 by 3. Then the last ratio cannot be considered, 3 by minus 1, because the denominator is negative. So 24 by 2 is 12, then 15 by 3 is 5. So this is the minimum ratio, and therefore we push this S2 out of the basis. So we have this column as the entering column and the second row as the leaving row, and the element in the junction, that is 3, is the pivot element. So we are going to make the next modification, that is, in the next modification S1 is in the first position, it has no change. Then S2 is getting replaced by S3. Then X1 also has no change in position. Then the cost of S1, cost of S2, cost of S1 as X1 is 6. Now we have to make suitable modifications so that this second, this column corresponding to S3 is converted to the second column of the identity matrix. So in order to make this 3 equal to 1, what we have to do is we have to divide throughout the second row by 3. So 15 by 3, it is 5, then 0, then minus 1 by 3, then 0, then 1 by 3, then 1. So let me call this as R2, and then we are going to make the modifications with respect of the other rows with respect to R2. So R1 gets modified as R1 minus 2R2. R1 minus 2R2 will make this as 2 minus 2, and hence it is equal to 0. So we have 24 minus 2 into 5, 24 minus 10, it is 14. Then we have a 0 minus 0, then we have 1 minus 2 into minus 1 by 3. So we have 1 minus 2 into minus 1 by 3. So 1 plus 2 by 3. So we have 5 by 3. Then we have 1. Then we have 0 minus 2 by 3. So we have minus 2 by 3 here. Then we have 0 here. 2 minus 2, it is 0. Now R3 gets modified as R3 plus R2. R3 plus R2. So we have 3 plus 5 equal to 8. Then 1 plus 0. Then 1 minus 1 by 3. It is 2 by 3. Then we have 0. Then we have 0 plus 1 by 3. It is 1 by 3. Then we have 0. Now let us have our objective function value. Z is equal to 0 plus 6 into 8, 48. Then we have net evaluation, 6 into 1 minus 6 equal to 0. Then 6 into 2 by 3, it is 4, minus 4, it is 0. See, it is 0 into 5 by 3 plus 0 into minus 1 by 3 plus 6 into 2 by 3, which is 4. Then minus the cost 4, it is 0. So the next net evaluation is 0. The next net evaluation is 2. The last net evaluation is 0. So we got all the net evaluations as greater than or equal to 0. So that indicates that the current solution is optimal. So we are going to conclude the solution. The current solution is optimal because we don't have any negative net evaluation. Now see, there is another important point here. We can see that the net evaluations corresponding to the basic variables are all equal to 0. The basic variables are S1, the net evaluation is 0. S3 is the next basic variable, its net evaluation is 0. X1 is the next basic variable, its net evaluation is also equal to 0. But there is a difference in this particular question. The net evaluation corresponding to a non-basic variable is also equal to 0. See the situation? The net evaluation corresponding to a non-basic variable. This x2 is a non-basic variable. Its net evaluation is equal to 0. Its net evaluation is equal to 0. and that leads to the existence of an alternate optimal solution. Alternate optimal solution may exist. So this indicates the net evaluation corresponding to a non-basic variable equal to 0 indicates the existence of an alternate optimal solution. Now, how to get this alternate optimal solution? Now, in order to get this alternate optimal solution, we can make this variable whose net evaluation happen to be equal to 0 enter the basis. Since we are not having any negative net evaluation, the solution is optimal, but the existence of net evaluation equal to 0 for a non-basic variable assures the existence of an indicates the existence of another solution, another optimal solution. So we are just going to find that alternate optimal solution. In order to get that alternate optimal solution, we have to modify this basis. Now, in order to modify that basis, we have to make one variable leave the basis, and in its place we have to make one variable enter the basis. So that entering variable is determined by this net variable whose net evaluation is equal to 0, the non-basic variable whose net evaluation is equal to 0. So hence we make the second variable, that is x2, enter the basis. Now when one variable enters the basis, as usual we have to pull one variable out of the basis, that is obtained, that is determined with the help of a minimum ratio rule. That is determined with the help of a minimum ratio rule, and we are going to compute that minimum ratio. It is 14 into 3 by 5, so that is the first ratio. Next ratio is divided by minus 1 by 3, that is not permitted. Then the last ratio is 8 by 2, it is 12, 8 by 2 into 3, so this is equal to 12. Now among these two ratios, the first ratio is comes around 8.4, and so this is smaller when compared to 12, and therefore we have to pull this S1, we have to make this S1 leave the basis. So let us modify the basis. So this is, we are going to get an alternate optimal solution. So we are making S1 leave the basis, and in its place we are making X2 enter the basis. So now the basis gets modified as X2, S3 and X1. So the cost of X2 is 4, S3 it is 0, X1 it is 6. Now the pivot element is this 5 by 3. In order to make this pivot element 1, we have to multiply throughout by 3 by 5. So our first element becomes 42 by 5, that is 14 into 3 by 5, 42 by 5, then 0, then 1, then 3 by 5, then next element is minus 2 by 5, that is minus 2 by 3 into 3 by 5, that is minus 2 by 5, then 0. Now we have to, so let me call this as R1 into 3 by R5, that is the modified R1. Now we are going to make the changes of R2 and R3 with respect to this R1. So R2 gets modified as R2 plus 1 by 3 R1, R2 plus 1 by 3 R1, and hence this S3 value becomes 5 minus 5 plus 1 by 3 into 42 by 5, and that is 11 by 5, then 0, then minus 1 by 3 plus 1 by 3, it is 0, then 0 plus 1 by 3 into 3 by 5, that is 1 by 5, then 1 by 3 plus 1 by 3 into minus 2 by 5, it is 1 by 5, and the last element is 1. Last element is 1 plus 1 by 3 into 0, it is 1. Now the next element in R3 gets modified as R3 minus 2 by 3 R1, R3 minus 2 by 3 R1, and hence by the corresponding changes, this 8 gets modified as 8 minus 2 by 3 into 42 by 5, and we get 12 by 5. Then we have 1, then we have 0, then we have a 2 by 3 minus 2 by 3, it is 0. Then we have a 0 plus minus 2 by 3 into 3 by 5, which is minus 2 by 5. Then we have a 1 by 3 minus 2 by 5 into minus 2 by 3, that is 3 by 5. And then we have 0. Now let us find the value of the objective function. Z is equal to 4 into 42 by 5 plus 6 into 12 by 5. 4 into 42 by 5 plus 6 into 12 by 5 will give you 48. Then 0 into 4 into 0 plus 0 into 0 plus 6 into 1 minus 6, it is 0. Similarly, the next net evaluation is 0. Then we have 4 into 3 by 5, which is 12 by 5 minus 12 by 5, it is 0. Then we have minus 8 by 5, then plus 18 by 5, it is 10 by 5. Now the next net evaluation is also equal to 0. So again we got all non-zero net all non-negative net evaluations, and hence this solution is also optimal. So this is the alternate solution. This is the alternate optimal solution. So hence let me write the solution. The solution is x1 equal to the first solution is actually x1 is equal to 8, x2 is equal to, x3 is equal to 0, and maximum Z is equal to 48. The second solution is x1 is equal to 12 by 5, x2 is equal to 42 by 5, and x3 is equal to 0. The variables that are absent in the optimal simplex table, they are just equal to 0 because only the basic variable appears in the basis. All the other variables will be having value equal to 0. So x3 is not present in the optimal table, and hence we have the value is equal to 0, and also maximum Z is equal to 48. So hence you can see that this maximum value will remain the same for different combinations of the values of x1, x2, x3. So we got two solutions, so one solution and the second solution. So both these solutions are optimal solutions. Thank you.